Alright, what's up y'all? We're about to do some more galaxy and cluster dynamics revision. Today I'm going to be sort of giving you an introduction into galaxies and sort of the treatment of them, galactic coordinate systems, that sort of thing. Before we begin, this is a capital theta, and this is what I look like when I draw it normal sized. Every time I see it though, I picture someone with like fat cheeks or something, like that. So keep an eye out for it later on, I guess. Anyway, so when dealing with an axis symmetric system, we need to define a cylindrical polar coordinate system, for obvious reasons. So here we've got Z going in the upwards direction, I guess you'd call it. North is positive for that. And then rotating around this Z axis is theta. And we've got clockwise as positive for that. And then in the radial direction, we use this little fella down here, pi. It's apparently pi, if you say so. So yeah, pi for the radial direction. That's obviously positive away from the galactic centre. We define the velocities using the same characters, just capitals. So big pi is d little pi by dt. Big theta is d little theta by dt. And big z is d little z by dt. Alright, okay. So now you also see here we've got this L on here. That's the local position of the Sun. But the Sun sort of bobs around in sort of weird ways. It doesn't trace out a perfect orbit around the galactic centre, as no stars do. So we define a local standard of rest, an LSR. This is the kinematical local standard of rest. So here we've got a beautifully drawn Milky Way. This is the galactic centre. What we do, we take the Sun as the origin at the moment. The Sun just happens to be on the origin at the moment of this local position. And then we take random velocities of all these stars. Oh, look at that focus. And we average all the velocities of these stars, and we find a sort of blob that's going to go bloop, 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 bloop. So, yeah, pretty good. Where am I going with this? Yeah, solar motion relative to the relative to this local standard of rest. We find that it's moving towards the galactic centre, so in the pi direction, about negative 10.4 kilometers a second. Sorry, the negative just indicates moving towards the galactic centre. Z 7.3 kilometers a second. It's moving up, so out of the page towards us at 7.3 kilometers a second. And we find theta to be 14.8 kilometers a second, so it's actually shooting around the galaxy a bit faster than most of the stars around it. So that's pretty cool. If we look at what's called the velocity dispersion of all the stars in this local field, which is the mean square random velocities. So that's this is the velocity dispersion in the theta direction. We find that that's about the same as the velocity dispersion in the z direction, where LSR denotes the average motion of local standard of rest. But we find it's only about 0.4 the size of the velocity dispersion in the pi direction, which is weird. So, put into words, this means stars have a larger random velocities in the radial direction. Stars have larger random velocities in the radial direction. Dun, dun, dun. Cool. Right, so moving on. We're going to define a different local standard of rest now. The dynamical local standard of rest. This one's a little bit better in my opinion, and we do use it more. So what you do is, again, you take a point that's currently coincidental with the Sun. Then you let the gravitational force equal the centrifugal force as it traces out a circle around the galactic centre. So that's the dynamical local standard of rest. Finally, we'll look at how this rotational velocity depends on radius. So how this velocity changes as a function of distance from the galactic centre in the radial direction. And we get this graph. So this is circular velocity. This is radius. The central region is largely uncertain, a bit weird. We see a sudden rise in the circular velocity at small pi. We see that the velocity curve becomes almost flat at large pi. Here we are sitting around about 8 kiloparsec. So we're at about 200 kilometers a second, I'd say. Lovely. That's the galaxy. Hope you enjoyed it. Went a bit better than the first one I did. I'm not shaking quite as much. Good night.